All right, let's get started. So far you guys we've worked with this bacterial model and the toilet model. In the bacterial model, we had to do a little bit of acrobatics because the bacteria, they're only discrete events that drove that system. So we had to turn it into a flow system by saying we're going to take the average behavior of the bacteria, divide it by the total number of bacteria, and pretend like each bacteria had an outflow that was continually flowing. And so we had to convert it to the average behavior and then take the average behavior and pretend like it was a continuous flow. Then the difference was, in the toilet bowl example, as you implement it in Excel, is that it actually has a true flow here. There's actually water flowing through the system. And so you have a state variable here, the water level, that could be at any one of the continuous states here. It's not an average level, it's the actual level. It's not like the average number of bacteria. Then you have a target, which is up here, which is fixed. That's an external parameter. So in our bacterial model, the external parameters were like the average lifetime of the bacteria. Here, our external parameter that's coming in is this target water level. And then there's a gap between these two, and then that gap ends up ultimately driving the water level up to the target water level in this balancing loop. And so in order to get there, we have to say, well, how does that actually happen? How is this implemented in real life? And in real life, there is a valve that is controlled by this, basically wherever this water level is, opens and closes a valve that brings water in. So there is a true flow of water that is modulated based on the difference between where the water level is and where you want it to be. And so we then incorporate that into the model by saying that this tank gap increases the flow of water, and then that flow of water increases the water level, which then will decrease the tank gap, and that's the full balancing loop. And so that's what you ended up simulating using that Excel spreadsheet. And the way that looked, so here's the causal loop diagram, and so ultimately we want to build a simulation of this thing. This is the stock and flow model of that. So this is our state variable, which is in a box. Here's our flow, which is we have stocks and flows. Our flow is this line here. We're going to go into all these definitions today. And then this tank gap is just there to help us connect the two of them. So we refer to that as a converter because it's sort of converting from this quantity to this quantity. And then we have other converters like this external variable that help us calculate what the tank gap relationship should be. So all of that comes together, and we like to simulate this system, which you've had experience doing now. So we have names for all these things. Like I said, we've got this target water level is going to be set to equal 15. This tank gap is just going to be a formula, which will be whatever the target water level is minus whatever the water level is. So you can already kind of see where these causal loop diagram polarities come into play with this tank gap. It's just this minus that. It shows you, kind of gives you an idea of what types of formulas will be in there. And then a flow of water, which in this case is just an exact copy of the tank gap. And then that determines this whole system here. And then what we don't see in this model is that initial water level, which is 0, so it's what we initialize the state variable at. And then also this time step thing. And we said this time step thing isn't actually a part of the physical system that we're trying to simulate. It is just a tiny little compounding period that allows our spreadsheet to be able to calculate row by row. Because there are no rows in real life when you flush a toilet, because it could go through a continuous string of time. But the computer has to think in terms of steps. And so in order for us to define what a step is, we have to say we're going to assume that the behavior is constant within this step size. And if we make that step size small enough, then we end up getting roughly a constant flow of water through in the real system, which allows us to approximate it as a truly constant flow of water in the simulated system, and then the two things are close together. So part of our challenge here is to pick a time step that gets small enough so that in the real system, the flows are roughly constant throughout that whole interval, so that when we approximate them as being actually constant in the computer system, it's not going to be that different. So that's ultimately what we've been doing with the spreadsheets. And so what hopefully you're able to figure out how to do over the weekend is to create a spreadsheet that kind of looks like this one, where you've got a DT, that's that one parameter coming in, and the water level coming in here. And then just like in our bacterial example, we've got columns that represent stocks, flows, and converters. And so we've got this time column, starts at time 0, water level starts at water level 0, and the tank gap, which is our converter formula up there, is just going to be whatever the current water level is, well, whatever the target water level is minus the current water level. And that's what you see in this formula here. B2 minus whatever the current one is, and that's this tank gap. And then that will end up getting copied over into this flow over here. And so that, at that point, that's all we need to model the system-specific, the toilet-specific formulas. All other formulas are going to look the same for any stock and flow model we do. We just set up our stocks. So we set up our initial stock levels, any parameters we have. We set up any converters, which help us convert from stocks to flows. And then we end up writing in the formulas for flows. Once we've done all of that in the first row, then we know we're just going to fill everything down. So like in the bacterial example, and I asked you to then build an outflow, it was tempting to try to say, well, I'm going to then go down in the lifetime of a bacteria and change the formulas down here. But the way these simulations work is all of the formulas are identical in every row. So you set up the first row, that's where you do all the modeling, and then everything else is a very formulaic, so you immediately get all of the other formulas out, regardless of knowing whether you know anything about the system or not. And so from here, like to get our time column, it's just going to be the previous time plus dt. To get the stock column, it's just going to be the previous stock plus the previous flow times dt to get our stock. And then the flow is going to be the same formula as before. The tank gap will be the same formula as before. So at this point, we can fill everything down and we can simulate the toilet, and we don't have to modify any other formulas. We can drag this down as far as we want, and like you'll see, then the toilet will get closer and closer and closer to this target water level. So those are the formulas that you would have implemented in that number 1 on, no pun intended, on the toilet example. So any questions about these formulas? Yeah.
I'm kind of a little bit confused on the different kinds of variables. Could you explain again what converters are? I get the flow is the rate of it, and the stocks are what we're actually measuring what the converters are.
Oh, that's a good question. So the question here is, what are these converters? I get what the stocks are and the flows are, but I'm not quite sure what converters are. And let me see if I gave my own definition here. So I also call converters auxiliary variables or parameters. So the idea behind a converter is that the only thing the simulation needs to go is a formula put in for the flow, because the flow tells you how the stock is going to work, and it needs an initial condition for the stock. The initial condition for the stock plus the formula for the flow times dt gets you the stock later. Once you have the stock later, you just go through the same process, and that gets you the stock later and later and later. So the stocks are the things where you just need to know where they are initially at, and the flows are how they change. The converters are just things that simplify the formulas inside here. So inside the flows, you could write a very, very complicated formula, and we'll get into this today. But the idea here is that I could take this entire formula, target water level minus water level, and put it inside the flow. But the downside of that is it doesn't give me as much insight into the system when I look at this stock and flow diagram. So rather than me just drawing a straight line between water level and flow of water, then I say, let's just create, to help the reader, another thing up here to say, by the way, I'm going to calculate tank gap. And this tank gap I'm going to use to calculate the flow. So it's almost like just a comment, it's a roadmap. It is sort of like, even though we could get directly from here to here, I'm gonna tell you where we're gonna stop along the way. We're gonna calculate tank gap first, and then with tank gap, we're gonna use that to calculate the flow. So then when I go to the spreadsheet, it's a similar idea here. I could have put this formula directly into the flow. But then you might not have understood, like if it just said flow of water and this subtraction, you might say, well, why that formula? By putting it this way, it communicates to me that, oh, you're calculating the gap, and then you're using that gap to figure out the flow. So it's just informational. The converters are informational. They're not necessary, but they make things more readable. And they help us, the main converter comes from them converting from one quantity, water level in centimeters, to another quantity, flow of water in centimeters per second. So I need some way to get from centimeters to centimeters per second, and so the claim is that I'm going to create a formula that if I was really being correct, I should have some multiply this by some conversion factor to make all the units work out as well. But this is just meant to be a formula to get me from one point to another. Does that help?
Yeah, would converter just be conversion from one variable to another?
You can say that. It is an explicit conversion from one variable to another. I could connect directly. I could put the formula directly here, but it is a separate formula I'm creating to make that conversion easier to understand for the reader.
Thank you.
So any other questions about this? It's basically the spread, yeah.
How do we know we have enough detail to construct a StockFlow diagram?
Well, it's easy, as long as you have a syntactically correct stock and flow diagram, you can simulate it. But the real question is, does it simulate anything useful about the real world? If you were to make the DT really, really small here, hit go, and the trajectory you get out of the water level doesn't look anything like a real toilet, then that suggests that you've left out some details. You've simulated something, but you just probably haven't simulated the thing you wanted to simulate. So that's very subjective, but that's the thing, is that we sort of come up with, in our mental models, we have an idea how these systems work. We put that mental model into a numerical model, then we hit go to see what the numerical model does. If the numerical model matches the real world, that gives us confidence our mental model might be correct. But if the numerical model is constructed correctly, we verified that, and it still doesn't match the real world, and that tells us we may need to update our mental model and see what we're missing. Anything else about these formulas? All right, well, if it comes up, we'll see. So after you do that, you get a bunch of numbers, and this water level should have increased continuously, and the flow of water should have decreased continuously. And if you were to plot both of them on this plot here, I got time on this axis, water level in centimeters on this axis, then I see the water level rises up to an asymptote around 15, and the flow of water falls to an asymptote of 0 starting from 15. And so this is what I would kind of expect. I only asked you to plot water level in yours, so if you only had this blue one, that's fine, just as long as you had the right labels here for time in seconds and water level in centimeters. But this gives us an idea of what's happening here. And this makes sense to us, because if you flush a toilet, it starts empty, like right after the flush, and then it starts rising up to a point here. And then the valve, as some people mentioned, I noticed in flipping through the submissions, some people mentioned that this simulation model actually never ever reaches 15. It just gets really, really close to it. It gets closer and closer and closer. It gets arbitrarily close, but it never actually hits 15. And in the real valve, if this were the real dynamics of the system, the valve probably cuts off a little bit before the water level, so that you never actually hit the target. You hit like something underneath the target. So it's almost as if the valve is being driven to a target, but then cuts it off early. And so that's more like what's really happening. So there's some what we call non-linearities that happen in the system that aren't being modeled here. But this simple so-called linear system captures most of the right dynamics. It just maybe doesn't get it quite right over here. But maybe what we really cared about was how quickly this rose and whether it had this particular shape. And so we're okay if it's not quite perfectly accurate out, at this point here. So any questions about this spreadsheet example? This is kind of the answer to the homework you just submitted. Yeah. Well, it's probably good that it doesn't reach 15. So ultimately that's a good thing, but the reason it doesn't reach 15 here is just because this formula for the flow of water, in order to have any positive flow, you have to have a difference in the tank gap. So if you're trying to totally close that difference off, bring it to zero, then your tank gap is gonna, be zero. So it's almost like you don't ever have enough inertia to get over the finish line. So it's kind of like, if you want to win a race, you have to aim to overshoot the target in order to actually, go faster than anyone else. Likewise, the way this system is designed, in order to win this race, it's like tortoise and the hare. It just gets closer and closer and never actually crosses the finish line. Heating systems at home, when you have this similar sort of feedback system, are designed to go over the threshold and then come back down, because they know that that's the only way that you can actually hit the target in a finite amount of time. And we could design those dynamics here. We just design them to be these dynamics, which don't go over the target. All right, any other questions about this interpretation? Yeah?
Can you go back to the formula for water level?
Yeah, water level is, so there's there's this right here.
Yeah, so
Okay.
when I first did it, I had it as B5 cells or B6 instead of B5, but I had it as B6 plus fixed B3 times C6, but I got the same answer. So I'm asking, like, in the future, if I did that with different variables, would it change it significantly?
So you had a fixed, the fixed B3 that you said, wasn't just because that we happen to choose different orderings of things that are up here. Was it that your B3 was your DT happened to be down here, or?
Well, I added a fixed value instead of multiplying it first, and I still got the same data.
Oh, so it was just you switched them
Yeah.
here? I mean, because multiplication commutes, it doesn't really matter which direction you do these, as long as it's the previous stock plus this. Now, because the initial water level was 0, if your first row didn't have this initial piece in it, it wouldn't make a difference. But you would need the accumulating effect in all the other rows.
Right.
So you would need this addition part later, but the order of these things wouldn't matter. All right, any other questions about the solution to that spreadsheet example? All right. So what you've simulated in a spreadsheet is effectively the calculus solution to this expression. If I were to replace these things like water level, if I instead of use water level, if I were to replace it with a variable, so I went and I made it X, and then I made this thing T, uppercase T minus X. So this would be X dot or X prime is equal to T minus X. Something like that. So this expression in calculus, you could solve that. You could take the integral of that thing. And so, you could have, taken the integral of T minus X dx from 0 to any time small t. And if you were to solve this expression, then my claim is that you would end up getting, and it's sort of written over here, another expression down here where the water level would be equal to the target water level times this expression 1 minus Euler's number to the e to the minus t. So it looks, it may not be obvious how you get from there to there, but my claim is that if you wanted to, we could go through it. There is a way to use a little bit of calculus to get from this expression to this expression. But it doesn't really matter, because if I were to plot that expression, I get exactly what we have here. So this blue line is the plot of this expression here, 15 times 1 minus e to the minus t. So by doing this Excel experiment, where we cut things up in these tiny little dt segments, where each water level is just the previous water level plus the flow times a little dt, that just basically arithmetic, getting me from one step to the next, gives me the same curve, this blue curve, that I would get if I used something more sophisticated like calculus to solve this integral. I'd end up getting this thing down here that if I plotted, it's identical to this. So that's why this is still, even though it doesn't feel like calculus, we're doing calculus-based modeling, because we're assuming that the models are being driven by rates of change, flows. Every time we draw one of these, we are implicitly writing a differential equation and asking the computer to solve it for us. So we don't have to do this. All we have to do is effectively the difficult part of writing the equation, which we can do in diagrams, but it's identical. And then after that, we let the computer do the rest. And so that's what we're getting here. So that's what I mean by, sometimes instead of calling this simulation, sometimes we call this numerical integration. And because going from here to here is asking the computer to generate an integral of the expression that we've represented diagrammatically this way. So that's what we're doing. So any questions about any of this before we go on to actually implementing these things in Vensim and Insight Maker? So you won't have to do the tedious steps of setting up these spreadsheets anymore. We just have to draw the diagrams and let Vensim go. Okay. All right, so let's think about what these flows are. So every flow is written as a, you can think of every flow, like let's say you a flow of 5. Well, what that means is that in one time unit, if that flow stayed constant, the stock it's attached to would move up by 5. So if the flow was this value, whatever the flow is, 5, 6, 7, whatever, if it was this value constantly over the whatever time interval you defined it at, the corresponding stock would rise by this stock amount. So if I called this 5, but I wrote it as 10 over 2, then that would mean if I waited 2 seconds, the stock would rise all the way up to 10. So that's the way we interpret what the heck a flow is. It's how much would the stock change if we left the flow this constant value for this amount of time. But in these stock and flow diagrams, the flows are changing very rapidly. And so this interpretation kind of only works for a tiny dt, and then the flow changes again. So in the case of our bacteria, we had to create kind of a fictitious flow. And we did that by creating these mean field models where we said, on average, a bacteria creates a new bacteria every W time units. And so we created a flow of the population which said every bacteria is going to take the W time units it takes to produce a new one, and we're going to spread that all over it so that you can see this flow comes out here. So this little flow rate per bacteria is just saying we wait W time units and get one more bacteria out. That's where the 1 over W is. And we multiply that by all of the bacteria. And so for the whole population, each bacteria is flowing out this amount of new bacteria. And so this whole population is bacteria divided by W. That's the inflow, the new bacteria coming in. And this tells us that if the population didn't change, then if we waited W time units, we would get a doubling of the number of bacteria. However bacteria we started with, if we waited W time units, we would get double them back. Now, we don't do the simulation that way because we know that as you get new bacteria, they start reproducing. But for the tiny little time unit, the DT time unit, we then make that approximation in order to calculate how much bacteria we get after that little DT time unit. So that's how we interpret this bacteria case. We take the mean behavior of the bacteria and smear them out over all the bacteria to create these flows. And so whenever you're modeling anything that looks like a population growth rate, could be the number of people in the Phoenix, for example, you can ask, on average, how long does it take every person to reproduce? Now, you might need to factor into that, not every person reproduces. And so you can factor the probability of reproduction in to this calculation, and you can say, on average, you have to wait this long in order to, if you start with a certain, with one person, you can kind of figure out, well, if that person's got a 50% chance of reproducing, and if they do reproduce, it takes them 10 years, then you can sort of say, well, then maybe it takes 20 years to get one person out because of that 50%. So you kind of think, what's the average time to generate one new person, and how many people come out of that? So for the one case, it'd be like 1 divided by 20. So whenever you think of these population systems, those are event-based systems, but we want to take the average behavior and smear it out over time, and that's how we get these flow equations. So then likewise for the death side of things, those are event-based, And so again, the individual flow, that tells me that I wait L time units, and on average, I get a reduction by 1 unit for every unit. And so the total flow says if I have this number of bacteria to start with, if I wait L time units, the lifetime of the bacteria, then on average, everybody dies. And so that's where I get this flow rate. But then behind the scenes, it's gonna only move 1 dt per time, and so it's not gonna just go whole L units and kill every bacteria. It's gonna go a tiny dt unit and scale this and say, all right, if this is the outflow, then how many bacteria died in this really, really tiny time unit? And after that time unit, it recalculates this. So that's what we mean by flow rate. So these instantaneous rates of change. And for population systems, the population death rate is normally going to be the number of individuals in the population divided by the average lifetime. That would work for Phoenix, that would work for the globe, that would work for a petri dish of bacteria. That's just the standard way to model the death rate in these population systems. So guidelines for population systems: measure the average time it takes for an individual to be added. Oh, yeah, sorry.
So for the thing, say like somebody's average, say the average lifetime is like 78, would that mean that we would want to put like 47?
Well, it's whatever the time, yeah, so if the time units of your simulation, and we'll get into this when we get into Vensim, if you've defined them to be years, then you just put 78. If you define them to be minutes, you put, however many minutes are in 78 years. But yeah, but that's the idea, is that variable, you look up, what's the average timeline, and say, on average, people live for 78 years, so that's what you configure as that L for a parameter in that bacteria model. So that's something, the guidelines, if I give you a population system, the way you're gonna build these stock and flow models, at least initially for the small little population component of the system, is you ask, how long does each individual live? An average of T time units. But then I'm saying that, okay, so then each individual contributes 1/T inflow per individual. And then I take that number of individuals times the per individual contribution, and this is my inflow into the population. And that works for any population system. The outflow, it's a similar process. And so the outflow is going to be how long do people live? Maybe it's L. And so for every individual, their contribution to the outflow rate will be 1/L. And then, so the whole population's contribution to outflow rate is going to be the number of individuals times 1/L. So my stock and flow model for my population, for at least the little population component of it, is going to have an inflow of 1/W, an outflow of 1/L, so the net flow is the number of individuals times 1/W minus 1/L. So that's how we start to form these. If you start with a population system, you're probably gonna have something like this buried inside your system somewhere. Now you can get more exotic with this. So you can say, well, as the population gets high, then maybe the death rate goes up because it's harder to find food. And so you can imagine changing these things, but this is sort of the basics of where you start. And we'll get to how you embellish things as we move on in the semester. But this is, the sort of the simplest, one of the simplest systems we model are these population systems. And so that's why I'm kind of spending some time looking at this. Any questions about how I formed this model of inflow and outflow into a population? It's all based on averages. How long on average do you wait to reproduce? How long on average do you wait to die? How long on average do you wait to leave the class? So then for this system, it's a little different, as I was explaining before, where we don't have any events anymore. Everything is a continuous movement. We don't need to worry about averages. So we actually are modeling the true dynamics of the system. It's not the average dynamics of the system. And so in this case, this flow really does mean that if I had a flow rate of 20 centimeters per second, if I waited 1 second and I left the flow turned on at 20 centimeters per second, the tank would rise 20 centimeters. Now I know I'm not gonna leave it on, like that flow is going to decrease over time. Otherwise, this would probably overflow, or at least might sometimes overshoot. And so that's why this flow is gonna change over time. And at any instant, that the instantaneous amount of water coming out of the valve here is going to be equal to, you know, it's a speed of water. The amount of water coming out of here is, if it held that speed, then if you left it on for the denominator, however, if you write this as 20, you get 20 over here by doing 40 divided by 2, and that would mean if you left it on for 2, then the rate with the level would go up 40. So that's the way we interpret this flow that's coming out of there. But the valve's rate is constantly changing, so that's why we don't see that after a second it jumps up 20. After a second it might be far less than 20 because the valve it'll slow down over time. So the guidelines here is for bucket-like stocks, like a toilet, then we need to know the inflow rate is generally written as the gap size divided by T, where T, and this is a little funny, is the time it takes for you to reach 63.21, so that's 6.321% of completion when closing the gap. And so there are some technical reasons why we chose this, but this is what's referred to as the time constant of the system. And so basically what we're saying is, because the flow rate is changing over time, if you're trying to model that toilet but you don't know how fast that valve closes off, you can flush the toilet once and measure how long it takes for the toilet to reach 63% of that 15 centimeters. How long does it take to get 63% of the way all the way there? And that time is what we use as the so-called time constant of the system that we can end up putting into our models. We can't use the time for it to, how long it takes to hit the level, because it may not ever hit the level. So that's why we have to use a time that's less than the level. And this value here, which relates to that Euler's number, ends up being a very convenient level to use. And so our flow rates are typically written as sort of gap size divided by T, where T here is the time it takes to reach 63% of the final value. And that's the so-called time constant of the system, time constant. So you'll just start knowing that number, that 63.21%, it's sort of equal to like 1 over E. I remember it just because 6 divided by 2 is 3, and then it's just 321, so 6, 321. But just roughly 63%, you use that. And so people ask, what's the time constant of the system? That's how fast does the system reach its target? And so you could say, when I'm modeling this, if I'm putting in a formula for the toilet, you could say, well, if my formula for the flow rate is gap size divided by 1, which is what you did in your spreadsheet models, because if remember, the flow rate was just equal to gap size, so it's implicitly saying it's gap size divided by 1. What you're saying is that it takes 1 second for the toilet to reach 63% of its travel. That's probably a little fast. It's probably the time constant of the actual toilet is probably a lot higher than that. So it's probably more like 5 or 6. It might take a couple of seconds to reach 63% of that total level. So if this is the top, this is it, and it starts down here. What we're saying here is that in 1 second it gets to 63%, but it probably takes 2 or 3 seconds. So when you're building your models and figuring out what parameter to put here, if it's a bucket filling system, you need to ask, how long does it take to reach 63%? And then you could do the gap divided by that time, and that will better fit the real system model. So that's just a guideline for these types of bucket filling components of your system. So there are questions of what I mean. Some of this will become more clear as we work with these types of systems, but I just want to at least introduce these in this lecture, these 2 types of systems, population systems and bucket type systems. Yeah? So why don't, or, well, you did, but you, so in the spreadsheet model, your flow rate was just equal to gap size. So you implicitly made your T equal to 1. So you were modeling a toilet that had a time constant of 1 second. And so my claim is most toilets probably aren't that fast. And so in a real toilet, the time constant probably would be equal to 5. Now, if I would have gone out and said to you in that assignment over the weekend, use the formula target minus water level divided by 5, then I have a feeling that a bunch of you would say, well, where's this 5 coming from? Why 5? So I just said, all right, we're just gonna make it equal to the gap. But qualitatively, that gave us the right shape. But quantitatively, that probably modeled a much faster toilet than reality. So now, as we move from qualitative models to quantitative models, we want to get a better fit to the real dynamics. And that means picking these times. And so instead of choosing a 1 like you did in the Excel spreadsheet, you're now going to choose values that actually match real data. So this becomes more data-driven. All right, any other questions about this idea of how to choose flow rates for these bucket filling systems where your stock is just filling up as opposed to being a population that is inflows and outflows? Okay. All right. So now we were ready to start building these stock and flow diagrams. So depending on what tool you use, then you're gonna have different icons for stocks. So this is like up here in Vensim, this is in a program called AnyLogic, this is in Stella, which is the tool that your textbook uses, and then this is in Insight Maker. So the common element here is boxes. Stocks are written as boxes. In fact, some software programs call them box variables. And they're shown as boxes because they're meant to look like buckets that can fill up. So stock represents anything that can accumulate, which is why it kind of looks like a bucket, because things accumulate in a bucket. So that's when we draw stocks. Stocks will have flows associated with them. They're just the rates. Again, Vensim, this is AnyLogic, this is Stella, and this is Insight Maker. The common element here is that flows are always thick arrows. Sometimes they have valves shown on them. Sometimes the valves are more embellished than other times, but sometimes they just look like thick arrows. So the thick arrow is the common element. They usually are pointing in one direction, but occasionally you'll see a flow that has an arrow pointing in the other direction. So you might see something like a flow this way, and then one of these arrows might be colored in, and the other one might not be. And the reason that they do that is sometimes you have flows that can go in both directions. And what they're trying to indicate is when you have a positive flow, it moves toward this arrow. But when you have a negative flow, it moves towards that arrow. And so when it has two arrows, they're just emphasizing to you that you could be pulling things out of the bucket or putting things into the bucket in both directions. Almost always, we're going to work with flows that just move in one direction. But you definitely can have flows that move in two directions. So if you look in your textbook, a couple of the models may look like you have two arrows here. And that's just indicating that it is possible to have a negative value in the flow rate, which would indicate that the water would come out of the bucket, like splashing out of the bucket, coming out the wrong way. So that's what that's about. These little clouds here just mean that the flow rate is unlimited. So a lot of times you'll put a stock on either side of the flow rates, but very often you just have a stock on one side of the flow rate and the other side is just open. And what this is saying, this cloud is saying there's always going to be enough material to fill whatever is on the other side of this flow. It's not going to be limiting on this side. So it's just an infinite amount of material, and that's what the kind of cloud is indicating. It's just a cloud of material. It's available for free from anywhere, and so you don't have to worry about this restricting the flow. So that's flows. And then the other thing are converters, and the common thing in all of these different tools here is they're often drawn as ovals or circles. And so the converter here, again, that's just a convenient place to put a formula to make your diagrams look better, and so you don't have to bury all the math inside a flow equation. You can break it out and make the causal loops more clear. And so sometimes they're also called dynamic variables, or auxiliary variables, and so on. So look for circles or ovals. And then you connect all of those with informational links, and these links, these thin arrows, tell you where you're allowed to put variables. And so if you have a stock or if you have something, a flow or a stock on this side, so it could be a stock called X, then putting this arrow here tells me that whatever I'm connected to here can use X. So if I have a formula over here and it's using a variable, that variable needs to be connected to that formula through one of these links. If it isn't, when you try to play or hit run on your simulation, it'll say you don't have access to that variable. So this is enforcing you showing graphically the dependencies. So this is saying that if this quantity depends on that, if you put it in the formula, you better show graphically that that dependency exists. And that's what it's enforcing by not allowing you to run the model if that's not there. So that exports the thing from this side into this side. So those are our different elements that we'll combine together. And you can use these like causal loop diagrams, so it's very common to annotate them with pluses, minuses, S's, and O's, and so on. It's not necessary in a stock and flow diagram, but I definitely recommend that whenever possible, annotate your stock and flow diagrams with causal loops. All right, so as a quick example, I've got 3 dynamic variables. Dynamic desired bank balance, gap between desired and actual, and all bank balances. And so at this point, I might, in this gap formula here, might want to implement this formula down here. Like I want to say the gap is going to be equal to desired minus all. But if I tried to implement that in Vensim, if I were to drill down in here and put that formula in there, it would say it's an illegal formula because I didn't draw the links. By putting the link here and the link here, then I turn it into a legal formula because Vensim is saying I have exported this variable to here, I've exported this variable to here, and now I can write the formula there. So that's the purpose of those links. Any questions about that? About these?
It's not gonna let us write the formula unless the graphic looks.
That's right. The graphic has to fit first, and then you can write a formula based on what the graphic allows you to do. So we're trying to capture in graphics. Remember, part of these tools is communication. So we're trying to better capture the essence of these formulas graphically before we implement the formulas. Yeah?
For those of us, sometimes we that don't know how to link them, would the formula help us get the links correct?
Yeah, absolutely. So if you put a formula here that uses these variables, that tells you that the arrow goes in this direction. So the arrow points toward where you need to export them to make the formulas go. Does that make sense? All right. So here's a quick example. So, so look at this up here and tell me what links are definitely missing in this. This is an attempt at a stock and flow diagram that's modeling the dynamical trajectories of a savings account balance and a checking account balance. And up here, we have all bank balances, which are supposed to be the sum of these two. We have our desired bank balance, and we have this gap between desired and actual. So what links are missing? So take 30 seconds and talk to your neighbor and tell me what links are definitely missing that I'm going to need in order to make this thing run. All right, let's bring it back in. So which links are definitely missing? Does anybody have a link that's missing that needs to be drawn in order to make this thing work? Yeah. All right, so we said, yeah, so the vote here is for savings account balance and checking account balance to both go up here in this direction. Anybody else come up with that? Nobody? Yes, okay, so those are definitely, in order to calculate all bank balances, I need access to the bank balances, but I don't get that unless I draw the links. So that's definitely was missing there. Another one that might be missing is in order to calculate the interest, I need to know the savings account balance. So that's another little trick there, is that this flow rate, the interest coming in, depends upon the savings account. And so I had to add that link there in order to imagine what this interest formula is going to be. Other questions about that? Does that make sense? That I needed both these links and that link to make this formula go. All right. Now, of course, you could add a bunch of other links to this too. So you could imagine that maybe the amount of money that you put into your savings account balance depends upon how much is in your checking account. So you could imagine adding other converters, other things that model how you manage these two accounts. And you could put those things in here. But just to get the basic model going, just like it's a basic population model or a basic toilet model, then we needed these links just to hit go and make it actually happen. All right. So annotating then. So if I've got this flow in this stock, like I said, these links you can think of as causal links, and it's always or often a good idea to annotate them with whether they're a positive or a negative, if it's obvious. So sometimes these formulas are very condition dependent, and so when the stock is high, maybe it's positive. When it's low, maybe it's negative. If that's the case, you maybe should think about, is there a way for me to break one flow into multiple flows so that there always is a consistent causal relationship? But if worst comes to worst, you can just omit these because they're not necessary. Now what I'm showing here is that the inflow always has an implicit positive causal relationship between the flow and the stock it's connected to. We don't often draw this causal relationship, but if you're trying to analyze the causal loops in a stock and flow diagram, you have to always remember that this is there, even though it may not have been drawn. Like this whole link may have been left out because it's chart junk, because you already have a thick arrow going this way. But there's an implied thin arrow going from every flow to every stock, even though we don't always draw them. Yeah, is that a question?
It's probably wrong, but you can't just put positive polarity on the thing.
You could put a little plus here. It's not traditional to do that, and a lot of modeling tools don't allow you to annotate the tips of the rates. They only allow you to annotate these informational links. Okay. Similarly, on the outflow side, and this is where it gets a lot of people confused at first, the outflow is a big thick arrow going out, but by default, an outflow reduces a stock. So if you increase an outflow, you decrease a stock. So there is always an implicit link coming back from an outflow that has a negative polarity. So when you're drawing a bunch of causal loop diagrams, this is when it's really easy to forget the first time you do this. So I might give you a stock and flow diagram, ask you to find a negative feedback, and you say, I don't see any loops whatsoever. Well, it might be the reason you don't see loops is because you left out this link right here. And that may end up closing some larger loop. So remember that even though it's drawn out, it's actually pointing in with a negative relationship. So that's a little counterintuitive, but I hope that makes sense. Are there questions about that? So this, when I draw an inflow and an outflow, I am always implying that these two things are there. But I very rarely actually draw them. So instead, I kind of just have to remember that there is, if I've got these real links coming through from stock to inflow, that there actually are feedbacks here, even though it doesn't look like they're feedbacks. So like this one here, I claim this is a reinforcing loop, because as the stock gets larger, it reduces the outflow. But you say, I don't see a reinforcing loop there. All I see are arrows going away from the stock. But I have to remember that there are these arrows that are coming back from the outflow. And so this is actually a reinforcing loop because there's a negative link here and another negative link here. So that's why this actually is a loop, even though it doesn't look like a loop, because there's that implied link coming back. Similarly, on this side, this is a balancing loop because there's an implied positive link going this way. This is a little easier to see because you've got it happens to coincide with the arrow that's already there for the flow. But you just have to remember there's an implicit loop there. So there's two loops being shown here, even though it only looks like outward going informational links. If it helps you, you could go ahead and do that. But eventually, it is not conventional to draw the implicit loops. You just have to remember they're there. Because once you start doing this a lot, you just naturally see them. And so people don't like to throw them on there because it's not conventional. If you were to draw it on there, and you're communicating to someone that there's something weird going on that they should focus on. But if you draw that link and there's not something like another converter down here or something like that, then people start wondering, why did you draw that link? I already know that that's there. So it's technically implied by the outflow. And so that's why we don't like to draw it, because it's redundant and it just confuses the reader. But initially, sometimes it's helpful to always draw those. So I'm okay with it. You can go ahead and draw it, but just know eventually you should probably get rid of those. All right. So our steps, if I give you a bacterial causal loop or bacterial stock and flow diagram like this one, then the first thing I want to do is I hopefully have annotated all my links, my real links here. And then I want to say, okay, so I've annotated them with appropriate polarity. So I've already done that. I know that as I increase the time to reproduction, it decreases the birth rate. As I increase the birth rate, it increases the births, and so on. So then my next step is to add those implicit links to make sure I've accounted for all of them. So I'm going to add them just on my, maybe I just pencil them in so I don't have to put them on the diagram, but I at least put them in when I'm doing my analysis. So that means putting both of them in there. And then the outflows are these negative links. That reveals feedbacks that otherwise I didn't notice were there. So I can label those feedbacks. And now I see, reinforcing followed by balancing. I recognize that motif. That's my S-shaped growth motif. So then I can say that, okay, so this is S-shaped growth. And so I can get rid of all the implicit loops, but I can leave the loop annotations on. So you usually put the implicit loops on just to remind you where these loops are, but then when you export it in a document or you put it in a report to someone, you get rid of the implicit ones, but you leave the annotations on, because that then tells the reader that, oh, by the way, in case you forgot, there's a reinforcing loop here, a balancing loop here, and those two next to each other, that's the S-shaped growth. And so that's how I expect this system to work. All right, are there questions about that? All right, so just so we can get to the Vensim, I'm going to move a little more quickly through here. But so like with this toilet system, it looks like it should be a feedback, or there should be closing the loop. I just have to remember this is positive here. And so that means that I've got a positive, a negative, and another positive. So I'd expect that to be a balancing loop. And so even though there wasn't this link drawn in there initially, I have to remember that the link is actually there. And so the balancing loop I get in the causal loop diagram, I can just show with a little balancing loop in this thing here. I don't have to draw the whole CLD, but I can annotate it just to remind someone that that is a balancing feedback. Okay. So questions about annotating your stock and flow diagrams? Yeah.
What was that weird thing?
This was just me kind of highlighting that hidden underneath here is this link here. All right. Okay, so let's now see how to do this in Vensim. So I'm just going to highlight a couple of the basics for getting these things up and running in Vensim. If you like to use Vensim, I also recommend you go to Unit D in Canvas, and I have a longer tutorial video that shows you, it's only a little longer, that shows you in more detail how to get started and to get running and to operate these things and export your data and so on and so forth. And so this will go a little quick, but you can find this tutorial online under the Unit D module. So if I go and I were to start Vensim, I get the blank canvas as expected. So if I go up under model and then settings, that is where Vensim stores its DT value. So if you all started Vensim and you went into model and settings, it's going to be hard to read here, but you can see that it has initial time, final time, and time step. And then it also has units for time. Those are like the 4 most important things that we end up messing with inside settings. There's a lot of other interesting things we can adjust here, but at least at this point, those 4 are the ones we really care about. So initial time, it's almost always going to be 0. Final time, if I tell you to go for 5 time units, that's where you put the 5 in that final time there. So I can go here and I can change that to a 5. Now when I say, what are my time units? There's a units for time down here, and it defaults to month. Month is not very useful for, say, modeling bacteria because they grow a lot in a month. And so I might be more interested in saying, seconds, for example, or minutes. And then the other thing is your time step. This down here where they've got a little drop down, you can also type in there, that is what we call DT in Excel. So it's so this is everything you've done in Excel, but it's just put in a different spot. So I can set this to 0.01, and I can go back and change it later if I'd like to. So to make things more visible, I'm going to right-click on the canvas and go and change my font size to something large, hopefully large enough to see. And now I want to just draw a simple stock and flow diagram. And so the first thing I do is figure out what my stocks will be. Up here, notice that they've got a boxed variable that they call level. That's what Vensim calls a stock. It's called a level. And so it's not meant level like a level, like a bubble level. It's meant level like the level of a water level. So I'm going to pull that level in, and I can create something here called like number of bacteria. And because of the font size, it got really compressed, and so now I've got a stock. So now I need to draw those birth rates and death rates, and I could, I'm going to truncate this a little bit, but I basically now can click on this rate, and that's what Vensim calls flows, rates. So I click on that rate, and from there, I can now click on a stock. So I'll go to rate here, and I can click on that stock, and then it shows me an arrow going out. And if I were to click on another stock, it would connect those two together. If I just click on the blank canvas, and then I can say, I'll call this deaths, or death rate maybe, then it puts one of those little clouds on the outside here. So then I want the other flow. So I'm going to go up to rate again. I'm going to click on the canvas, and now click on bacteria, and I can say, call this birth rate. And so now I've got a birth rate connected to the bacteria and a death rate connected to the bacteria. So now what I need to do is then put formulas in for these things. Now I could I could generate converters to make those formulas, maybe I want to create a variable out here called average lifetime. And maybe I'll drag that over here. And maybe then I can then connect this average lifetime to death rate. And I can connect number of bacteria to death rate. And that exports the number of bacteria to the death rate. Likewise, I can create a variable called time to reproduction. Maybe I'll put it down here and do the same thing. And so now all that's left is me to actually put the formulas in. So in Vensim, once I'm done with all of that, up here, notice there's an equations. If I click on that equations, it highlights in black everything that's missing an equation. So I can go through and I can click on average lifetime, and in the little blank field here, I'm going to say the average lifetime is, and I forget what we did, I think 3 in the spreadsheet. Time to reproduction, I think we did 0.75 in the spreadsheet. The birth rate, if I click on that birth rate flow, it shows me everything I've wired up to it. And it says you've wired up number of bacteria and time to reproduction. Well, if I remember my birth rate, it was just number of bacteria divided by time to reproduction. So I can go down and I can either type those in manually, or I can just click down here, and I see number of bacteria, and I hit slash for divide.
How do you get that big box?
You just hit the little, you hit the equations up here, the little f of x. And then when you click that, then you can click on any of the flow and the stocks and the variables, and it'll open this thing up.
Thank you.
So that's where I can implement the formula that I would implement inside my inflow in Excel. And I do the same thing for outflow. And it again shows me all the things I've wired up. Number of bacteria, average lifetime. If I remember for the bacterial example, the outflow is just number of bacteria divided by average lifetime. So that's what I'm putting in the formula. And I can click OK there. The only thing left now is this stock. Now we don't put a formula in for the stock, but we have to put the initial value of the level. So if I click on that, it will show me that it has a formula already put in. It says integ. This shows me that it's about to do an integral. But down here, initial value, that's where I need to put something in. And my initial number of bacteria in the bacterial example was 1, so I can put a 1 in there. And so now everything is, back to the normal color, which tells me I have a formula for everything. And so I'm ready to run this simulation. To run the sims, you can go up and just hit the simulate button. Now in Vensim, when I do that, it's asking me if I want to save. I'm not going to worry about saving it right now. It looks like actually I have to save on this computer, so I'll pick a folder to save it in. So this will be bacteria. So maybe I'll try that again. So if I simulate, it looks like nothing happens. What just happened is it simulated the whole sort of spreadsheet, and it stored it in a data file, and now I have to ask it to show me what's in that data file. And I do that by looking down down this side here, where it has things like graph and table. And if I click that, like let's say I click graph. If I were to first click on number of bacteria and then click on graph, it now shows me the number of bacteria. If I wanted to plot two things at once, I could have clicked on highlighted multiple things like birth rate and number of bacteria. If I click on graph, it now shows me both of those simultaneously. So it did all that stuff for me. Now you might say, this is great, but I don't like these plots the way they look. I would like to plot these in Excel. I want it to do all the work generating the data, but then I want to do the plotting. Well, in that case, you don't have to generate the graphs. You can go over, and there are these two things here, table and table time. So I'm going to click on table time, and this basically gives me exactly what Excel gave me. It has a time column down here where everything's separated by DT, and then it has a birth rate, which is that flow going in, and then it has the number of bacteria right here. And I can take that, and if you look really closely in the top, there's a little save box, and you can save it out as a text file. That text file you can then open up in Excel and plot it. So you now have the ability to plot these things and do whatever embellishments you want on your plot. So you can get a quick plot out of Vensim and then a much nicer plot when you export it to Excel. And those are the basics of how you run one of these stock and flow diagrams in Vensim. So I want to do that same thing quickly, at least to get started in Insight Maker. But are there any questions about how to do this in Vensim?
The video that you said
Goes into more detail. Yeah. And you will, I've got an assignment here for this week where you're going to re-implement the toilet model inside Vensim. and Insight Maker. So I'll just put maybe, just pass these around so you can take a look at those. And you know now what the toilet model is supposed to output, and so you should be in okay shape. All right, so let's say I don't like to do it in Vensim. I'd like to see what it looks like in Insight Maker. So what I'll do now is I will open up Chrome, let's see. If you go to insightmaker.com, and if you've already created an account, you should be able to log in to that account. Now, my issue is that I actually don't remember. I didn't think about this ahead of time. So let me see if I can guess. All right. So, so because I have a feeling I'm probably not going to be able to guess this, and I don't want to take the time to create a new account out here. Let me try one more thing. All right, so for Insight Maker, it's a very similar process, and you know, maybe on Thursday I'll do the quick Insight Maker demo. For now, there is a video online where if Vensim isn't working so well for you, then you can try Insight Maker. It's roughly the same idea. It's a little different in how you create the flows. You have to draw a flow in one direction, and then there's a switch direction button to get it to move the other way. So that's the only sort of big difference. But otherwise, you get graphs the same way, and you can export table data the same way. And I go over that in that tutorial. But I'd like to sort of, let's see, let's make sure we cover everything here. Any questions then about Vensim? And again, I can give you a quick Insight Maker tutorial next time, but I want to at least make sure you've seen Vensim now that I've passed out that assignment. So any questions about that or about Vensim? All right, so just where we go from here. So the final project, if you haven't seen it, there is slides online on in Unit D. I put them under Lecture D1 as well as under the final project module. There's a couple of slides giving you all the deliverables for the final project. The first deliverable to worry about is, I think, the Saturday after Lecture E1, so that's basically in 2 weeks or so, or you just have to form your teams. So there's a Canvas assignment, it's already available online, where every team member submits the names of everybody in the team. So I'm sure everybody's in agreement. So start forming your teams. You know, there's the thing about, you know, when that should be available. And then the next thing after that is you'll write a short proposal, which is what system you're going to model. And that's like a couple weeks after you form the teams. Keep reading Chapter 3. The next lecture, we're going to go over Chapter 3. So there's an assignment online, and then there's also going to be one of these assessments in class, and then we'll talk about that. And that's when Moorcroft introduces stock and flow diagrams. Create a free Insight Maker account. Make sure you remember your password, something that I forgot to do. And then we've got this new assignment. The midterm, again, is coming up. So I've already talked about this. There is study guide stuff for the midterm already online. Inside each unit, I've got these topic outlines. I recommend looking through those, but then also the study materials that I've put and the kind of practice problems that I've put under the midterm. Then this assignment that I just passed out, basically I'm having you re-implement the toilet model in Vensim. I have some requests here for you to plot your water level, the diagram of your stock and flow model, as well as give me all your formulas. You always usually plot your formulas next to your stock and flow diagram. In number 2, you're going to add a continuous leak to that toilet, and then for extra credit, draw a CLD of the whole system, including the leak. And so that's basically what things are going to look like for how you start this thing. So any questions? All right, so for the attendance exercise here, then I said that in these bucket filling systems, we usually define them by something which is the time until the system reaches 63% of its target value. What name did I give for that time? I said it's a parameter, it's something somebody would ask you, what is the this of the system? So that name, it's 2 words. The first word is time. And so it is the time until the system reaches 63.21% of its final value. That is called something. What is it called? It is a constant that starts with time. All right. That's all I've got for you.